Hi everyone. Today I will present the work View Object Reconstruction with Unknown Categories and Camera Poses. This is a joint work by Hanwen, Zhenyu, Kristen, and Yuke from UT Austin. Accurate and scalable object reconstruction method can unlock diverse applications. We can spawn the reconstructions in mixed reality for immersive experiences. We can make the 2D internet more 3D aware, like better online shopping systems. We can use reconstructions to build diverse and realistic simulations as digital twins of the world. In this work, we focus on view object reconstruction. Here is a demo of our method illustrating how it's like. In this setting, the model takes in a few images without posing information, and it produces 3D model reconstructions. Let's dive deeper to the reason why we want to explore view object reconstruction, especially towards accurate and scalable reconstruction methods. Let's have a look at the data we can access nowadays. The data can be divided into three parts: single view, field view, and dense view data, with different data quantity and quality. For single view reconstruction, we can easily get large amount of data, which can be scaled. However, they are usually in low quality with occlusions and low resolutions. Moreover, the problem is ill-posed, where the unobservable part of the objects limits the reconstruction quality. For dense view reconstruction, the data collection is hard to be scalable. Besides, the dense view method typically requires slow optimization, which limits the real application. Field view images have the advantages of both. We can still get scalable and high-quality data from the internet, or they can be easily captured. Moreover, the field view images solve the ambiguity problem in most cases. Here is a comparison between the mentioned settings. Then the question arises, can we build a method for field view object reconstruction which is scalable and accurate? Unfortunately, there's no method can do this, and prior works have problems related to the use of camera poses. The first kind of method assumes the access to ground truth camera poses. Different from the dense view setting where we can use co-map, camera pose estimation from field views is far from being solved. Thus, the assumption is not realistic. The second is assuming the prior knowledge of object categories by setting the canonical spaces. It improves the pose estimation accuracy using the prior knowledge. However, it limits the scalability. They cannot generalize to novel object categories as their canonical poses are not defined. To eliminate the canonical space, we estimate relative camera poses. In this setting, the relative transformation between the two cameras is always well defined, even for unknown categories. Thus, the model can be scaled to any object categories. We introduce our method, Forge. Forge takes in a few unposed images. It then predicts the relative camera poses between images and fuse the per view 3D features into a neural volume reconstruction. Then we can render novel views and supervise the model with rendering losses. In detail, we set the first image as the canonical view, which has an identity pose. We then use a voxel encoder to get per view 3D features, which are defined in the corresponding camera coordinate frames. We use both 3D features and 2D images to predict the relative camera poses. We then perform 3D rigid transformations on the 3D features using the predicted poses. In this way, we transform the features into a shared reconstruction space. We then fuse the 3D features and predict the neural volume. A key component of Forge is the camera pose estimator. To boost the pose accuracy, we build two pose reasoning modules, which takes different inputs. In the pairwise pose reasoning module, we calculate the 3D correspondence cues between each pair of 3D features. This module benefits from the use of accurate 3D-aware features. In the global pose reasoning module, we build 2D feature maps, where each feature element aggregates information from all other views. Thus, the model has a global understanding of the camera configurations, which helps when the overlap between an image pair is too small. In experiment, we perform stage-wise training. As the pose estimator is dependent on accurate 3D features, we first train the model using ground truth poses. Then we learn the pose estimator with reliable 3D and 2D features. Finally, we fine-tune the model end-to-end. On ShapeNet, our method Forge demonstrates better performance compared with prior works using ground truth poses. The performance with predicted poses is also reasonably good, where we show some visualization results. Besides, the model generalizes to unknown categories with very small performance gap. Forge also achieves better post-estimation accuracy, reducing both rotation and translation errors by a large margin. We show visualization below. We also include results on real datasets. Please check our paper for more details. Forge has some surprising good properties. First, it demonstrates zero-shot generalization to novel real objects. Good geometry reconstruction emerges without using any 3D supervisions for training. In conclusion, Forge is the first method that works on field view inputs without camera poses and general object categories, and it demonstrates good reconstruction quality. However, it's a complicated system which is not scalable enough, especially the post-estimation designs and stage-wise training. Thus, in our following project Leap, we found we don't need camera pose estimation. Instead of using camera poses for linking up 2D pixels and 3D spaces, we can learn attentions to assign fusion weights adaptively. Thus, we build a model with standard transformers, and it is an independent discovery of large reconstruction models. We have release code for both Forge and Leap. Please refer to our project page for more details. Thank you.